Those are limits that are infinite in nature. What about more ordinary kinds of limits? Oh, let's do a real simple one. How about the limit as x approaches 4 of, how about 3x minus 7? So this is a new example. There's a new function here. This is my f of x function. Hey, a nice simple function. Its graph's a straight line. Hey, we're not letting x go to plus or minus infinity, just 4. What should this limit be? Shouldn't it just be what we get when we plug in 4 into the function? Shouldn't it be? I mean, it's so simple, right? There's no holes in the graph. Yes, just plug in 4. To get 3 times 4 minus 7 is 12 minus 7 is 5. Done. I like that kind of problem. Is it really right? 3x minus 7, line with a slope of 3 and a y-intercept of -7. Looks about like this, say, and when x is 3, the function output is certainly 4, but is the limit 4? F of 3 is certainly, not 4, 5. F of 3 is certainly 5. Oh, 4, sorry. Why was 3 and 4 in my head? Maybe because that 3 and that 4, I don't know. F of 4 is certainly 5. Does that mean the limit as x approaches 4 of f of x is also 5? Yes, because it's a nice continuous function. That's why. When you're thinking about this limit, the technical definition says, think about the function outputs. Okay, this is not super technical. It's still kind of hand-wavy. Think about the function outputs. What are they getting closer and closer to as x gets closer and closer to 4 without actually equaling 4? Why without actually equaling 4? Because that's what we want to do in the case when functions have holes in their graph. That's why. And functions with holes in their graphs are actually important in calculus, like I hinted at last time, for derivatives. When you're computing a derivative using a limit, as we will very soon, you're computing a limit for a function whose graph definitely has a hole in it, as strange as that sounds. It's not the same as the original function that you're computing the derivative of. It's a related function. And if you have no idea what I'm talking about, it's okay. We'll get there. The point I'm trying to make is functions whose graphs have holes in them are actually essential to think about in calculus. They are not mere curiosities. But this function, f of x, this linear function, doesn't have any holes in it. So the function outputs, as x gets closer and closer to 4 without actually equaling 4, do indeed get closer and closer to 5, which is the function output when x is 4. Say that again. We're saying again. This limit, technically speaking, you're asking what happens to the function outputs, f of x, the y values, as x gets closer and closer to 4 without actually equaling 4. The second coordinates, these green points that I'm making, as you approach 4 in the x direction here, are getting closer and closer to 5. In fact, I can make them as close as I want to 5 by making x close enough to 3. That's analogous to getting above any horizontal line by making x close enough to 3 from the left, -3, with the other example. Yeah, they get closer and closer to 5. And in fact, the limit truly is 5 because this function doesn't have a hole in its graph. I can find this limit value by plugging in 4 because it's a continuous function. This is because f of x is continuous. Because f is continuous at 4, technically speaking, at x equals 4, though it is also continuous everywhere. What does continuous really mean? Continuous intuitively means you can draw the graph without picking up your writing utensil. Intuitively. Now, of course, you eventually have to pick your writing utensil up because eventually you have to stop drawing the graph. Pretend you can draw it forever. Okay. If you can draw it forever and ever without picking up your writing utensil, then it's continuous everywhere. If you have to, at some point, pick up your writing utensil, not counting the fact that if there's a hole in it, you might argue, well, I can draw the hole without picking up my writing utensil. No, if there's a hole, you have to pretend you pick up your writing utensil. Not counting that, then it's discontinuous. If there's truly a hole in the graph, it's discontinuous at that point where there's the hole. Like the example from last time, and like an example I'll go ahead and make right now. What's an example of a function with a hole in it? Let's use this same function. How about a rational function 3x minus 7 over 3x minus 7 times x plus 1. I purposely put a 3x minus 7 on the bottom again. Does this limit as x approaches 4 exist? Or, okay, let me change what x is approaching. Let me let x approach 7/3. Maybe you can figure out why I'm letting x approach 7/3. Does that limit exist? Technically speaking, this function is undefined at 7/3. You'd be dividing by 0. 3 times 7/3 is 7, minus 7 is 0. Does it have a limit as x approaches 7/3? Possibly. Could it also possibly have a vertical asymptote? Also possibly. You have to cancel the common factor to help you figure it out. That function that I started with, 3x minus 7 over the product of 3x minus 7 and x plus 1 equals this function as long as x is not equal to 7/3. Equal if x is not equal to 7/3. Therefore, their limits will be the same as x approaches 7/3 if this one has a limit when x approaches 7/3. And it does, because you're not dividing by 0 when you plug in x equals 7/3 there. This is continuous at 7/3. The only place it's not continuous is -1, right? I can evaluate this limit by plugging in 7/3. Get a common denominator of 3 in the bottom, you'll get 10/3 in the bottom. This limit is 3/10, 0.3. Don't believe me? Try graphing it. And for fun, let me go ahead and graph it by plugging in my calculator with the bottom expanded even. FOIL, 3x squared plus 3x minus 7x minus 7. The bottom can be 3x squared minus 4x minus 7. It's the same function. Did I do it right? No mistakes? Okay, let me plug it into my calculator that way. 3x minus 7 on top. Divide by that quadratic, 3x squared. Having trouble here. X squared minus 4x minus 7. Let's plot this. Oh, say from -4 to +4. Let me make my tick marks on the x-axis, say 1/3 of a unit apart. It'll help me find 7/3 better. The answer seems to be 0.3. A function value is fairly low there. Although in general, I think the function could go high. Let's just see what the graph looks like here. Yeah, vertical asymptote at -1. When x approaches 7/3, this is 1/3, 2/3, 3/3, 4/3, 5/3, 6/3, 7/3, right about there. The y coordinate is getting close to 0, close to 0.3 perhaps. Let's trace. 7/3 is 2 and 1/3, right? Yep. We're getting close there to 7/3. Y, yes, is close to 0.3. But technically speaking, you want to be extra technical about it. The graph has a hole in it at 7/3. There's a point missing because you can't plug in 7/3 into the original function. You can plug it into there. But technically, lots of technicallys today, technically that's a different function. They're the same function everywhere except 7/3. They're equal as long as x is not 7/3. This one is defined at 7/3 and it equals 0.3 there. This one's not. It's got a hole in its graph, but their limits are the same. I know I'm being real intense today. I'm trying to get across really important points. I'm trying to really emphasize things. It's not an easy subject. You might wonder also with this, what's the limit as x approaches -1? Well, if this graph is correct, in either case, these functions are equal close to -1, but not equal to -1. They're both undefined there. It looks like x goes to +infinity as you approach -1 from the right, and down to -infinity as you approach -1 from the left. And you could think about this factorization in positive, negative quantities in it by imagining x to be close to -1, either on the left or the right. So there's an example of a graph with a hole in it. This function has a graph with a hole in it, a point missing. Of course, the calculator doesn't know that. Calculator is a dumb machine. By the way, just because we have artificial intelligence these days doesn't mean it's smart. AI is not necessarily smart. It's good at gathering lots of data and analyzing that data and producing what seems like smart output, but it still is programmed. Yes, it does quote unquote learn, but that doesn't mean it's smart either, okay? It's still a dumb machine just doing what humans have programmed it to do. And in this case, it's plotting points and connecting the dots. That's all it's doing. So it doesn't know there's a hole. Question? Yes, good point. This function, I'm talking about the original function, is continuous everywhere except -1 and 7/3. Those are the 2 points of discontinuity for the original function here. This other function is continuous everywhere except -1. It is continuous at 7/3. This function would have a graph that would have no hole there. Make sense? Looking at the formula? No problem dividing by 0 if you plug in 7/3. We got 0.3. This one, you can't plug in 7/3. Subtle distinctions, but important. Yeah, neither of them can you plug in -1. Yeah, when you've got a hole in a graph like this, that means it's called a removable discontinuity. It's kind of like a dumb discontinuity. It's like, why bother with the hole? Why not just fill it in? And you could, but if you did, it's really this function instead of that function. Or you could do this function and make it a piecewise function where you also define it to equal 0.3 when x is 7/3. That's another thing you could do. If you did that, if you made this a piecewise function and define it to equal 0.3 when x is 7/3, it's really the same as that function. Even though you might say it's got a different formula overall. The outputs for any given input are still the same. So it's still the same function. It's expanding your mind, realizing other new possibilities. I hope so. Is there ever a case where a function might have a hole in its graph, but then be defined to be something else at that value of x? Like maybe when x is 5, maybe this holds at 4 and the output up here is at 6. What if that was your function? Does that ever happen? Well, okay, let's worry about what to do if that was your function. If this is your function, does this limit exist? And if it does, what is equal? Is it 4, is it 6, or is it neither? Nobody want to venture a guess? Mm-hmm.
Limits are always.
The limit would be 4, you're correct. You said it partially correct, but not quite. Yes, you're right. The limit is whatever it's approaching as x is approaching 5 without actually equaling it. But it's not that it never equals that. It would if it was continuous. So this limit is 4. The outputs as x approaches 5 from either direction are getting closer and closer to 4. I can make them as close as I like to 4 by letting x be sufficiently close to 5 without equaling it. That's why the limit is 4. But that does not equal 6, which is the function output when x is 5. And because of that, that means this function is not continuous at x equals 5. Therefore, 3 dots means therefore, f is not continuous at x equals 5. That's a point of discontinuity. It's continuous everywhere else, but not at 5. Now you might say, well, why would you ever do that? That seems dumb. Why not just make f of 5 equal to 4? The answer is, yeah, in most applications, that would be a dumb thing to do, but conceivably, I'm not going to say what. Maybe it's a good idea. Okay. Could I think of an application? Kind of. Pretend you got a function that looks like this, that's 0 for all x, except when x is 0. And when x is 0, it's, I don't know, 5 or something. What kind of real life thing could this be a model of? Probably nothing perfectly, but approximately it could be a model, for example, of hitting a nail with a hammer. It's called an impulse force. Essentially, you're hitting that hammer so quickly, it's almost like it's occurring at just one instant in time. At time 0, you hit the hammer with whatever, 5 newtons of force or whatever, okay? Actually, it's a little funny. You can look this up if you like. Hitting a nail with a hammer in this context is sometimes modeled by a function that's 0 everywhere except 0, and at 0 it's up at infinity. Wait a minute. What? It's almost like infinite force at an instant in time. That's why it's called impulse forcing. And if you want to look it up, it's called the Dirac delta function. And it's almost like you're treating infinity like a number when you do that, even though infinity is not a number. So confusing. I'm telling you things like this to intrigue you. It's not that you have to know them for the test, okay? There's something called the Dirac delta function, where infinity is kind of treated like a number, and it's kind of 0 everywhere except one point where it equals infinity. That's not rigorous. It's an idea that you have to try to make rigorous. There are ways to make it rigorous.
Well, wouldn't that require your hammer to have either velocity?
Well, you might argue, yes. You could maybe get away with a finite mass hammer hitting it truly at one instant in time, but that doesn't really happen in reality. So it's only an approximation. Okay. These kinds of things are intriguing to people like me. Like, how can you possibly do that? You can look it up. You can look up videos. Maybe 3 Blue 1 Brown's got a video about this. 3 Blue 1 Brown is a great YouTube channel having great math content. I'd highly encourage you to go there, including his videos about calculus. They will give you good insight into things.
I think he has done a video about piecewise functions at some point.
Yeah, I'm not sure about the Dirac delta function, though. It wouldn't surprise me if he's got it, though. What other kinds of things do you encounter with limits? You encounter functions where maybe the limit exists from the left and from the right, but you get different answers. Huh? Here's an example. And let me even make it piecewise to make it defined everywhere. Let f of x be the absolute value of x divided by x if x is non-zero, and 0 if x is 0. That is a function you can see is defined for all x. If x is not 0, plug into that formula. If x is 0, the output is 0. F of 0 is 0. If x is positive, the absolute value of x equals x. Right? Absolute value of 7 is 7. So the absolute value of x over x is x over x is 1. If x is negative, the absolute value of x is negative x. Huh? How can that be the case? I said negative x, but maybe I should have said the opposite of x. Just because there's a negative sign in front of a number doesn't mean the entire number is negative. Like if x is negative 7, negative of negative x is positive. Negative of negative 7 is positive 7. The opposite of 7 is 7 itself, if you prefer using the word opposite. The additive inverse of the additive inverse of 7 is 7, if you prefer using the phrase additive inverse. So we get this, which simplifies to -1. This function has a graph that equals 1 when x is positive, -1 when x is negative, and is 0 when x is 0. It is defined everywhere, but it's not continuous everywhere. It's discontinuous at x equals 0. It's continuous everywhere else. Does it have a limit as x approaches 0? It's got one-sided limits. If you let x approach 0 from the left, the outputs are always -1. So the limit is -1, not 0, even though f of 0 is 0. When I think about the limit, I'm not letting x actually equal 0. So the outputs stay at -1 the entire time. The limit as x approaches 0 from the right. Let x approach 0 from the right, the outputs always stay at +1. This is +1. That's also not equal to the function value at 0. But it could have. I could have put a 1 there instead of a 0. I could have done that. It would have been a different example. Then it would have been equal to the function value at 0 if I had done that, if I had made that a 1. So this function does have these one-sided limits. One-sided limits. They are numbers, but they don't equal the function value at 0, so the function is not continuous. But they're not equal to each other. This is not an 11 with a slash through it. It's a sideways equal sign. They're not equal to each other. Therefore, the two-sided limit, which is what this notation means, where I don't put a minus or a plus sign to the right, does not exist. Can you write equals does not exist? I won't mark it wrong if you do, but I tend to just write DNE for does not exist. And it doesn't equal plus or minus infinity because it's not going up forever and ever or down forever and ever. The one-sided limits are not equal. Therefore, the two-sided limit does not exist. Question? What kind of functions do you do this? Is that what you're asking? You can think about one-sided and two-sided limits for any function you're given. Okay. I'm just thinking about it for this example. Could such a function have any applications? Almost. I think I'm thinking of like turning on a light switch. Effectively, the light's off, you turn it on, and then it's on. I mean, that doesn't account for this point in the middle, but it's almost like a model for that. Okay, like the electrical output of the light. Almost out of time. Let me show you one more example. And this is the most wild example of them all. I guess we're not getting to Mathematica today. We will for sure on Friday. I will make sure of it. What's the limit as x goes to 0 of sine of 1 over x? Calculator, help me, help me, help me. Sine of 1 divided by x. Let's try our original window here to begin with. Just see what we see. Well, I'll go -1 to 1 here. Hard to tell. Let's zoom in closer to x equals 0. Even harder to tell. Let's zoom in even closer. Even harder to tell. What in the world? Zoom in even closer, one more time. Yikes, what in the world's going on? Part of what's going on is calculator error, actually. The calculator is not graphing it actually as accurate as it could. Could I make it graph it more accurate? Possibly, but I'm not going to take the time. What's really happening with this function is it's oscillating infinitely often near 0. Infinitely often, infinitely many oscillations up and down. And the calculator is saying, help, I can't do it. This limit definitely does not exist, and it does not exist in a very, very strange way because of infinitely many oscillations of equal amplitude. Amplitude 1 the entire time. Question?
So at like x equals 0.5, it cannot, or
I'll let you think about it. It oscillates infinitely often near 0, not near other points.
oh, all right.
Okay. All right. Have a good day.